Thank you, Daniel, and I want to thank Muriel and Nikos for actually allowing me a chance to speak here. I'm substituting for Steve Moises, and this is work that I am going to present that I've been doing in conjunction with him, Stephanie Werner, who is at the University of Oslo, Soko Matsumura in Dundee, and Shigeru Ida at ELSI. So there's one person at ELSI, Hidenori Genda, and he always starts his presentation with the conclusions. And I really like that because then you basically get the take-home message and everybody else can then doze off for the next 20 minutes. So the take-home message is that we think that the bombardment intensity on the Hadean Earth is actually much lower than what most people have thought that it was, and I'll show you why. These, of course, has implications for the early Earth's habitability and the dynamics and the origin of life and so forth. But the picture, basically, that it was a constant bombardment and you bury the Earth in impact melt is actually not correct. We also think that what we call the Late Veneer was actually caused by one very big impact about a lunar-sized object, rather than that it was a rain of planetesimals that was constantly pummeling the terrestrial planets. And last, the bombardment rate does not actually really conform to some of the modern simulations that we do from planet formation, such as, for example, the Grand TAC. So we can actually start to rule out certain models of terrestrial planet formation. I will not really go into detail this because this audience is more, this is a more specific topic for a different audience, but I will just mention that here, and that is something that we can then keep in mind. So generally it is thought that in order to create a habitable planet, or an inhabited planet as I would like to say, you need to have three ingredients. You need to have liquid water, you need to have some sort of free energy, usually a disequilibrium that tends to exist at the surface, for example, and you need to have organic raw materials, which we saw yesterday are created in quite an abundance in outer space, and then some of that will rain down on the terrestrial planets from comets and asteroids and so forth. So the hypothesis is, and this is something that we're also discussing at ELSI, basically when you have all three of these together, you will emerge some sort of biosphere, however primitive it may be, and it may actually be rather easy. And as we all know, the solar system formed, and we saw this yesterday, and I'll also speak more about this on Friday when I'll substitute for Sean Raymond's talk, is that the terrestrial planets are essentially formed through the coagulation of smaller bodies, usually planetesimals. Pebble accretion is a different scenario. And, you know, a lot of these bodies have evolved. So you start, for example, from the kind of disk that you see here to something that looks like the solar system. I apologize, the white lines are actually not showing up. I do not know why. So the small bodies evolve into planets of different types. And could these small bodies, actually have been the first habitats? And the reason we ask this question is because we see a lot of organic materials in asteroids and maybe even in comets as well, as we saw yesterday. And that then brings me to the topic of the one thing that most people, or at least some of us, do not always think about when we want to create an inhabited or habitable planet. The fourth ingredient that you need, apart from water, disequilibrium energy, and organics, is time. We need to have time for the system to actually evolve to some state where we can start to create the biosphere. And so, you know, the timeline that we usually have for the inner solar system is at 4567, so a few million years after the birth of the sun, you start to form the CAIs and chondrules. Then you have differentiated bodies like Vesta after about 3 to 10 million years. Mars accretes in about 5 million years. Actually, this is an older picture, but Mars should have been here, according to what Nicolas Dauphas has been saying. You have the giant impact that forms the moon at about 60 million years. You have the Late Veneer here, which I'll get to back in a moment. You have continental crust here, and the LHB peak may have been here, it may have been earlier. That is actually a topic still of debate. So you can start to form life, I think, perhaps as early as here. And we have the giant impact here, we have a little bit of accretion afterwards during the late Veneer, and we have almost next to nothing during the late heavy bombardment. So what we have been doing is we've been looking at the late Veneer and we defined two epochs. So the first epoch is the late Veneer epoch, which starts by definition at the moon forming event, which we peg at 4.5 giga-annum. And then it lasts until about, you start to see evidence of crust formation on the terrestrial planets. So for the Earth and for the Moon and for Mars, this tends to happen at about 4.42 billion years. The oldest lunar zircons are 4.4417, the oldest one on Mars is 4428. So it's about the same age. And then the late accretion epoch, we say, is from 4.42 until 4.25. That is roughly when we think the late heavy bombardment may start. 4.3, 4.2, 4.1, those are the numbers that are flying around at the moment. So we're basically just going to say that's somewhere in the middle. And I will talk about highly siderophile elements in a moment. So as you know, the Earth's late Veneer is actually being hypothesized because we see these highly siderophile elements in the Earth's mantle. So these are usually platinoid group elements such as platinum, gold, iridium, and these kind of guys. And because they're highly siderophile, they would actually like to sink into the core. So the moment these were accreted, usually if the planet is molten, they will just dike through the silicate mantle and they'll go straight into the core. So the fact that we actually see some of these highly siderophile elements in the mantle tells you that they must have been delivered after core formation, okay? And what you can then do is you can say, this is a study that Bill Botka has done, is you can then basically look at how much mass you accrete in order to explain this concentration of highly siderophile elements. I'll get to that in a second. And then you can look at how many bodies of a given size you need to accrete onto the planet in order to be able to explain the highly siderophile element concentration. Apologies. So what Bill did in 2010 is he said, okay, what is peculiar is that if you look at how much of these highly siderophile elements are in the Earth's mantle versus how much you have in the Moon, the ratio is a couple of thousand, which is weird because the gravitational cross-section is of the order of 20. So, and if you take gravitational focusing into account, you can maybe bump it up to 100 or something if you're lucky. So what he then did is he ran Monte Carlo experiments where he bombarded the Earth and the Moon. And he concluded that if you want to be able to explain this high ratio, you need to have bodies that follow a shallow size distribution. So most of the mass is in the big guys. And they need to be big, so there need to be a couple of, 1,000 kilometers or some. The largest guy needs to be of the order of a couple of 1,000 kilometers in size. And then you have this stochastic accretion, in which you basically preferentially target the Earth, and then you won't hit the Moon. And the way you can think about that is as follows. Imagine you have a loaded coin. So you have a coin which comes up heads 95% of the time and tails 5% of the time. If you throw that coin 20 times, you expect one tail and 19 heads. But if you throw the coin 5 times, the probability of getting a tail is very, very low. It's much lower than 5% because you're dealing with small number statistics. And that is actually what goes into this thing here. Because you have only got a few of these bodies around, then the probability of impacting the Earth becomes much, much higher than 95% rather than targeting the Moon. So during the late Veneer, we know from these highly siderophile elements that the Moon accreted about 0.025 weight%, which is like 3 times 10 to the minus 6 Earth masses. The Earth accreted about 1 weight%, so the difference is something like 2,000, while you expect it to be 90 from gravitational focusing and the ratio of the cross-sections. There's almost no late Veneer on Mars. It's still being debated. Kevin Reiter says there's nothing. People like James Day and so forth say that Mars also accreted about between 1/2 and 1 weight%. So what we're going to say is, okay, fine, we're going to actually then make a prediction as to what the late Veneer component on Mars is going to be. So what we then did is said, okay, so since the moon is the anomaly, that is going to be the odd one out. So in order to understand really what happened, we need to then say, okay, we're going to peg the late Veneer mass on the moon, and we're going to run Monte Carlo experiments where we bombard the Earth, the moon, and Mars simultaneously with planetesimals and see if we can reproduce this very high ratio of accretion between the Earth and the moon and see what predictions it makes for Mars and for the early habitability of the Earth. So our Monte Carlo simulations are very simple. You basically generate a planetesimal according to some size frequency distribution with a maximum size of 2,000, maximum diameter of 2,000 kilometers is what we started off with. Then from n-body simulations, we know what the probability of those planetesimals is to hit the Earth, the moon, and Mars. So that goes in the code. So it's basically if P is less than, let's say, 12%, you hit the Earth. If not, then you try to hit the moon or Mars. If not, you add the mass to the total mass and you generate the next planetesimal. And you do that until the moon has accreted about 3 times 10 to the minus 6 Earth masses during the late Veneer epoch and half of that during the late accretion epoch. So it's a very simple code, it's very simple to run, it's a very simple experiment. And then, so then the outcome is plotted here. This is, the horizontal axis is the mass, the ratio of the mass accreted by the Earth versus the ratio of mass accreted by the moon, okay? And the beige region here is where I want to end up, because that is what we observe from the highly siderophile element ratio between the Earth and the moon, at least from their mantles. And this is the cumulative distribution of that ratio. So you see that it's absolutely hopeless, right? It's very difficult for me to actually be in this beige region. It's less than 1% probability. I'm at the 99% of the cumulative probability. If I then look at how much mass I accrete onto the Earth, then I can actually find out how much of that, what is the threshold that would cause 50% wholesale melting of the crust. Right? And this is something that Oleg Abramov and Steve Moises and David Kring looked at in 2013. And it turns out that if I accrete a little bit more than about 2 times 10 to the minus 4 Earth masses, because this is in weight percent, so a little bit more than 0.02 weight percent on the Earth over, let's say, 100 million years, is enough to cause 50% of wholesale melting of the crust. Now that is inconsistent with the geochronology, because we have evidence from terrestrial zircons dating back to about 4.4 billion years old from, John Valley and people like that, that show that the Hadean Earth was actually had a temperature and a distribution a temperature distribution that was lower than what you find at mid-ocean rich basalt. So you cannot have caused a lot of wholesale melting of the crust after about 4.4. So that sets a strong constraint on how much material you can actually accrete. And then if we look at Mars, of course the dots are all over depending on how much stochastic accretion occurred on Mars and if it was hit with a few big guys. But generally we're at a couple of, we're at about 0.01, 0.03, 0.05 weight percent. So it's very, very low. And that might explain why it's so difficult to see a signature of a late Veneer on Mars. And last, we can make a prediction about how many planetesimals we should still have flying around in the system after the moon forming event. And it turns out that it is a few by 10 to the minus 3 Earth masses, which is an order of magnitude lower than what most n-body simulations, such as the Grand TAC, would predict. So in other words, in the summary of that Monte Carlo experiment, you cannot correct the terrestrial lunar HSE ratio at 99% probability if the maximum size of your planetesimal is 2,000 kilometers. The leftover mass is about an order of magnitude lower. The Earth accreted about 0.03 weight percent. If you accrete much more, you melt the crust, or too much of the crust. And we predict that Mars accreted after the moon forming event about 0.05 weight percent. So because we cannot reproduce that ratio, what if we increase the maximum diameter of the planetesimals to 4,000 kilometers? This is something that Simone Marchi did back in 2014. And then we get a distribution that looks like this. So yes, now I can do it at about the 5% level, but the mean mass that I now accrete is much higher than would cause the wholesale melting of the crust. I could have a late Veneer signature on Mars, and my leftover planetesimals are now also, a factor of a few higher, which is more or less consistent with what we predict from terrestrial planet formation simulations, such as the Grand TAC. However, the difficulty with this is, and this is what Simone Marchi published, is that if you have such large planetesimals flying around with a diameter up to 4,000 kilometers, and if I do my Monte Carlo experiments, I reproduce his result, which he said that the Earth, the Hadean Earth, would be buried in more than 100% of impact melts. Which is crazy, because I just told you 5 minutes ago that Hadean zircons show that the Hadean Earth was actually rather clement. So you cannot have had such a huge flux and a huge bombardment intensity at a time, because it is inconsistent with the geochronology. So what is our way out? Because we're faced with incompatible constraints. On the one hand, we want to have the larger planetesimals around so that we can reproduce the accreted mass ratio between the Earth and the Moon, but at the same time, we don't want them around, because then we reset too much of the Earth's crust and we bury the Earth in too much impact melt. And we thought one of the solutions that we could think of was that the late Veneer was caused by just one impact on the Earth. Just one big guy. Like a lunar-sized guy, which is about 1% of the Earth, just smacks into the Earth, and you have almost no background planetesimal flux after that, And the reason we say this is also, if you look at the bombardment intensity that we advocate, it's very difficult to melt anything above about 1,000 Kelvin, 1,000 degrees C, which is roughly the temperature you need to reset zircon. Okay, so that's why we're advocating a very low bombardment in the beginning. And then the late Veneer could have been caused by a guy like this. So you have an Earth with a core and a mantle. You have something that strikes the Earth that also has a core and a mantle. The core material from the impactor has all these nice, highly siderophile elements. It hits the Earth like that, and you end up with a fiery rain, and you can suspend all of these highly siderophile elements into the mantle of the Earth. This is something that we're writing up at the moment. So now that we have kind of constrained the bombardment for the Hadean Earth and said that it could not have been very intense, what kind of implications and predictions can we make from that? So this is where we brought Stephanie Werner on board, because we felt that if we want to make predictions with the bombardment, then we should be able to test that. And one of the best ways to do that is look at the lunar cratering record and see if we can actually reproduce that. So here is essentially the chronology of the lunar basins, depending on whether you use the NHON chronology, which is one of the curves that you can use for dating the basins, and the other one, the bottom one, is using the chronology that Stephanie Werner has developed. And the salmon band is essentially our late Veneer epoch, and the beige band is the late accretion epoch. So with the NHON chronology, we produce a couple of basins here, and then all the basins come later. And with the Werner chronology, we actually form most of the basins here, and a few come after. Now, the largest lunar basin is South Pole Aitken. And its age is contested, but we think it is older than 4.2, and it may be as old as 4.4. The projectile that most likely created the South Pole Aitken Basin had a diameter of roughly 200 kilometers, a little smaller than that. So what you can do is you know how much mass you accrete on the Earth, and you can then basically look at what is the largest projectile that accretes onto the Moon for my Monte Carlo simulations that actually reproduces what we see. So here you can see that we only have a couple of basins, maybe anywhere from 3 to about 10 basins in this late accretion epoch. Here the moon's had still in the magma ocean phase, so we can't really count the basins, but in this time we can. And you can see that if the largest projectile is about 200 kilometers, I reproduce anywhere from 0 to about 10 basins. So that is roughly consistent with the number of basins that we see during this particular epoch. And that then leads us to a new revised lunar cratering chronology. So the NHON chronology goes like this, which is an exponential. The Veneer chronology is a little lower. And we're saying that during the Late Veneer and the Late Accretion epoch, this is the contribution that you get from terrestrial planet formation simulation. So this is much lower than what is actually inferred from the lunar cratering record, which suggests that there should be an additional component, there should be an uptick somewhere between, let's say, 3.9 and 4.3 giga-annum, which then brings that curve to somewhere between the Veneer and the NHON curves, and then we decay like this. So what we're saying is that the early bombardment, the bombardment on the Hadean Earth, was rather low because you didn't have a lot of mass from terrestrial planet formation lying around. And then if you want this curve to be consistent with the chronology on the lunar cratering, you need to have an additional component which comes later, although we don't really know when. This is my penultimate slide. So the implications that we have for the Hadean Earth environment from this bombardment is that because the bombardment was so low, there were no substantial barriers for forming life. And because the giant impact of the moon occurred at about 60 million years, and then you rain out most of the atmosphere and so forth, and you form a crust a couple of million years later, we think that you could have actually started to have some primitive life and prebiotic chemistry and so forth about 100 million years after CAI formation. So at about 4.45, 4.4 giga-annum or something like that. The last thing I want to then say is that the giant impact that caused the moon forming event was much more intense than the Late Veneer. And the Late Veneer itself, which I just showed you, was much more intense than the late heavy bombardment which came after. So, you had only magma ocean events in the very early stage, and after that, the early Earth was much more clement. And this is my last slide. So this is, the kind of picture that we envision for a conceptual model for the Hadean Earth. So you have abundant small continental masses, like island arcs in the ocean and so forth, and like things like Hawaii and the Senkaku Islands and whatever. Yeah, I'll stop here. Thank you.